Testing, testing, test, test, test. Share screen.
Yeah. But she's such a good collector. She is a collector. Well, I'm the older son. Struggle. Better now.
Okay, how you guys doing? Struggling all around? Life's a battle, huh? Physics?
Yeah.
Oh. Gotta go to STEM. Fridays. I don't know. It's on the door. I think he's in the afternoon. No. I think he's in the morning, and then El Reza takes over in the afternoon. Mansour's really good.
Yeah.
But Stephanie's really good. She's there, you know, like today, I think. Yeah, there's some great tutors. Riley's also very good. Yeah. So I went back to this with El Reza. He was really confused about what's the difference between a frame and a machine. And now that you've seen them, basically a frame has at least one multi-force member, right? So when you have something like this, where you got, you know, that's a truss. That's because, and you know, all the loads are applied at the pins. But if you put a load like here, then it becomes a frame, because now you have a 3-force member. There's still some stuff you can, you know, do. Yeah, 3 forces on a member. Yeah, then it's a frame. So that guy right there is a 3-force member because it has forces applied here, here, and here. So no, they were all trusses. Yeah, the loads are all applied at the pins, so they're all trusses. Last week was all trusses. This week they're all frames, but some of them, like the backhoe, has, you know, parts where you do have, like, you could do the method of joints here at this point here. Can't erase that. But this guy there, that's sort of a method of joints area. But you know, the other parts, you've got to draw that guy and, you know, label all the forces internally to it. So we did this one together, and then I did this one kind of fast. So I don't know if you wrote this down. Should we do this one again? Because that was kind of fast at the end. Want to start with this one? So you've got this guy, whoops. Well, this one where where we only had, excuse me. No, I always have a little congestion, allergies and stuff. So this guy, you know, which has one multi-force member, and this kind of shows the difference between a multi-force member and a 2-force member, right? We did this yesterday. The 2-force member only has one unknown associated with it. It's only got forces applied at those pins. The forces have to be oriented in the direction of AB. So all I got to figure out is the magnitude and the sign. whether it's compression and tension. That's really simple with two force members. But with BC, because you got this third force applied in the middle, that makes it a three-force member, meaning that the forces are no longer, collinear like they are in a two-force member. They can be pointing in different directions, and in general, you're going to have three unknowns on each three-force member. In some cases, 4 unknowns, which we're going to look at in this one. So here's that slight addition to the basic idea of the last one by adding another force. Of course, we bent it a little bit, so it's not exactly the same topology. And we want to find the reactions that the pins exert on the frame at A, B, and C. So each pin, we got to figure out what's going on at each pin. And as we're used to by now, we know that there are the pins at A and C are holding that thing together. So they could potentially give a CX and a CY. And, if a point of, distinction or whatever, if this 1 kilonewton force was not there, that the force would be oriented along the line from A to B. It would sort of just be one unknown again, right? If it was only, if it was just this this member going to that joint there, then there's only one unknown, because the direction AX and AY would be proportionally scaled so that they would point along the line from A to B. So the only unknown is the magnitude. When you add that force there, then you have a separate AX and an AY. And it's no longer going to be collinear, oriented along the line from A to B. So, so we draw the diagram of the members, and then we apply the equations of equilibrium on each member to solve for the 6 unknowns. So there's 6 unknowns here, and we have to figure out the strategy to solve them. And so, so we're going to, question? What was Ha about? We did this one yesterday. But I did it fast, and so I think not everybody wrote it down, so we're going to do it again. So the, the member AB is drawn, and the member BC. We split this thing apart. We presume there's going to be an AX and an AY. I found out, I did a little more research, what's going on with this stupid thing. It turns out it looks like it's PowerPoint 2016. It's not the hardware, it's the software. So I think I'm going to buy 2013 on eBay. It's really annoying. I can't stand it anymore. It's driving me crazy. Yeah, I can't annotate it though in Google Slides. Yeah. PowerPoint that has the annotation feature. There are some other annotation options I could try to explore, but I think the easiest thing for me would be to just get A13. So the question about what's going on at B is if you, if you got this force here, 1,000 newtons acting in the middle, this is a 45-degree angle, then it might make sense to think of a BX going to the left, pushing B to the left, and a BY pulling it up. Certainly, if you do the moments around A, you're going to need something there at B to keep the thing from being pulled in a clockwise direction by that 1,000 Newton force, right? So either BX or BY is going to have to do that. And then on the other guy, we have this 500 Newton force, which is about a third of the way over. And the BY has to be equal and opposite, right? So that's the thing that carries over from one member to the other. You got to remember to switch the signs of those things. You're going to get sign errors. And this is 0.2 meters. This is whatever. You can see that all over there. So it looks intimidating because you got 4 unknowns there. We don't really expect to be able to solve those. However, when you write the equations for both halves, you can realize that the bx and the by, they show up in both sets of equations. So those can be actually manipulated further to eliminate bx and by. So we look at member AB and write the equations of equilibrium. And the sum of the moments at A, for instance, equals moments about A. You're going to have a bx times 0.4, and that's positive because that's going to give you a counterclockwise sense, right? And you're also going to have a by times 0.4. And you're going to have 1,000 times 0.2 going in the negative direction. Actually, that's on AB, and then on member of BC, you can do the sum of the moments at C. Question? Negative what? No, positive, right? Positive 500 times 0.4. Again, we're keeping the counterclockwise being positive. And what else? Isaac, what's a moment about point C? Keep going. By itself is not a moment though, right? So complete the moment for what is the moment that by is providing around point C? Yeah, what's the moment? What's the torque that it's providing about point C? Yeah, and is it positive or negative? Okay. David? How about another one? Negative bx times 0.4, right? Mm-hmm. Yeah, so you can kind of see you have 2 equations with bx in it, right? That's the nice thing. So 2 equations, 2 unknowns, you can solve that. So you can add these 2 equations together, and the bx's cancel out. You get 1 by, right? Bx times 0.4, and you get minus 1,000 times 0.2 plus 5,000 times 0.4. That equals 0, right? So by equals 0. And since by is 0, then you really have to solve for bx. You can take any of those equations and solve for bx and find that bx equals, say, 500 newtons. Because by is 0, then bx times 0.4 has to equal 200. So therefore, bx equals 500 newtons. That makes sense. So we're just adding those 2 equations together, and the bx's cancel out. The BX's cancel out, making it pretty easy. Now, if the loads had changed, that the BY equals 0 is a coincidence of the fact that the moment arm for that 1,000 Newton force is half of the length of the moment arm for the 500 Newton force about its other side, right? So if those forces were different, then you could see that BY would not be 0. So you could get different answers. Isaac? Uh-huh. BX is positive in the first one and negative in the second one, so can you just solve by what? Yeah, you could. However, I think it's easier to add the equations. If you add you vertically add them, right? And the BX's cancel out. That's what I did. So we added the equations here. So this is BX minus BX, which adds up to 0, right? So, and then this is BY times 0.4 plus BY times 0.6, which gives you BY. And this is 2,000 minus, or 200 minus 200, so that gives you 0. Right, so therefore BY plus 0 equals 0. Therefore BY equals 0. Okay. Well, that's just BX and BY. To get the other guys, we would also need to solve for the sum of the fx's. And so again, at AB, the sum of the fx's equals 0 gives us AX minus 500. What? AX minus, well, yeah, because BY is 500. BX is 500. AX minus 500 equals 0. So therefore, AX equals 500. And sum of the FYs equals AY minus 1,000. So therefore, AY equals 1,000. And then on member BC, same idea, sum of the FX's equals BX, which is 500 minus CX. BX, it's 500, and then minus CX. So therefore, CX equals 500. And the sum of the FYs equals 0 is going to equal BY, which is 0. So basically it's going to be CY minus 500. So therefore CY also equals 500. And those are the 6 answers. Okay. Question, Matthew, question?
Yeah, why isn't the AX minus 5, right? Why isn't the sum of the forces in the X for AB AX minus 500?
Because BX is 500.
Oh,
it's AX minus BX, and BX is 500. Mm-hmm. Yeah.
So, the moment equation, and the way I'm looking at it, you said that it was counterclockwise positive, right?
Uh-huh.
So I see that the 500
Yeah. You had a hard time determining whether it's counterclockwise or not?
Yeah.
Okay, here's what I want you to do. You've got a water wheel at sea, and it has all these veins on it. And you have a stream flowing this way. Which way is the water wheel going to turn? Yes. It's really simple. A little bit of imagination is all you need to figure out which way it's going to turn. Yeah, that's the point, right? And this is the thing. If there was a lever here, then it would start to spin this way, right? Yeah, this is, nobody should make these errors. People still do, but it's really easy. Just a little bit of imagination. Imagine it moving, which way is it going to turn? Any other questions? So then we have an attention quiz. Are you paying attention? When determining the reactions at joints A, B, and C, what is the minimum number of unknowns for solving this problem? Good question. 6. Anybody think 6? Jose, what do you think? Look carefully. Choose wisely. This is going to be like on the final. You're going to go, oh my God, what was it? Remember that. What's the distinction? What's the difference between this one and this one? No, there's only one force on that one, right? So what is member BC? Yeah, what do you call it? BC, what do you call BC? BC is a two-force member. What does that mean? There's only one unknown. So the answer is, sorry? A, 3. Okay, you're really stumped. What are you going to do on the test? You're going to draw a free body diagram of each member, right? What's the unknown on BC? FBC. It's either a tension or compression force. It's like a truss. It only has one unknown, right? So because you have this 500 force here, and you got a load here. So whatever this guy is, it's a two-force member. So therefore, it can only apply a force at B that's oriented along the line from B to C. The angle is given as 0.8 and 1.2. What is that? Is that 3, 4? No. Theta is the arctangent of 0.8 over 1.2. The angle's known. You know the direction, you just don't know the magnitude. So there's one unknown there, and then that's the same unknown at C. So if you're trying to find the reactions at C, it's the same FBC going this way. Well, I mean, I guess that's the pin. I mean, C is doing the same thing to the member as the member's doing to B, right? So this FBC is here. This is the pin pushing on the member. It's going to be in compression, right? And this is the member pushing back B. So if you drew the member BC, you would have this guy going there, FBC going this way, and FBC going this way. It's all the same angle. And you would have an AY and an AX. So those are your 3 unknowns. Right, so you're going to remember this, right? I love that we're doing this on this is your final exam. This is going to be so awesome. Guys, I don't know. Well, there's at least about a bank. The bank has about 160, so. Oh, I think it's, I don't know. I have to look it up. It's on canvas. It's about, it'd be probably about 30% or so, yeah. Yeah, about 30%. So I want you to leave this class with this stuff. You got to take, you have to be living and breathing this stuff, right? Because this is what you're going to be doing. This is it. You want to be an engineer, you got to know this stuff. Why are you laughing? How are you going to succeed if you can't remember this stuff? This is like the most important thing you can do. Everybody, when they get back to me, they go, oh my God, there's so much statics. For the above problem, imagine you have drawn a free body diagram with member AB. What will be the easiest way to write an equation solving the unknowns at B? Sorry? So in the moment at A. Sum of the moments at A equals 0, right? Yeah, because the, well, what about the FYs? Can we do it using FYs? Not really, right? Yeah, to find the unknown at B, yeah, you want to do the sum of the moments at A. Because only B, the B is only unknown there, right? If you do the sum of the FYs, you're going to have a B component and an A component. Some of the FXs, you're going to have an A component and a B component. So yeah, you're only going to have 2 unknowns there. But if you do the moments at A, then the only thing that gives you moment at A is the 500 Newton force and the force FBC. Okay. Good. Now, I think this is on the new sheet, right? It's still the old sheet? Wait, we're way behind. So pulleys are actually pretty straightforward. This is a block and tackle. It looks a little strange at first, but when you get to, again, it's the same principle. When you want to figure out what's going on with these things, these are machines, right? It's a machine. And you draw the diagrams of the pulleys, and you apply the equations of equilibrium and solve for the unknowns. So in this case, what are we doing here? Oh yeah, so this guy, we're going to draw the free body diagram of the pulleys, and we got to find P to hold that 1,000-pound load. We got a 1,000-pound load with this pulley system. It's really kind of fun, and what you do is, just like you break apart a frame, you can cut the ropes on a pulley. And if you cut the ropes on the pulley, you draw the free body diagram of each part. So the first pulley has a bracket, and it's going to have this thing here. And let's see, I think, yeah, something like that. And you're going to have this guy, and this guy, and this guy. Now, these are ropes, and you've cut them all. And yet, because this rope is continuous, it's only one rope, right? And they didn't say this, but these are actually, these have to be frictionless pulleys. And if it's frictionless, what does that tell us? If it's frictionless, what does that say? Rope tension is the same everywhere. In other words, no matter where you cut it, that rope has to have the same tension, right? If you had one long rope and you're pulling on it, right, and you know, if you had a rope attaching, you know, something from A to B, and you had some load on it, and you know, the tension would be everywhere. If you cut it here, you're gonna have the same tension everywhere, right? Well, just because it's in a pulley, if they're frictionless pulleys, it's the same way. The frictionless pulleys just communicate the tension all the way through the rope. It does not change anywhere. That rope has the same tension throughout, no matter where you cut it, which simplifies the analysis, because that means you've got a force P pulling down over here. You got a force P pulling down over there, and you got a force P pulling down over here. And, and then therefore you would have a force of 3P pulling up. The bottom pulley is going to help us out to find numbers, because right now these are just P's, so that doesn't really help. 3P, is 3P. This is just equations of equilibrium. But the bottom pulley has a rope like this, and a load here, has 1,000 pounds pulling down. And what's the force pulling up at these points? P again. So for the bottom pulley, the sum of the Fy's has to equal 0. And that's going to equal 2P going up minus 1,000 going down. So therefore, P equals 500. Questions? So you'll have some pulley problems in the homework. Basically, it's like that. Pretty easy. So a concept quiz. The figure shows a frame and its free body diagrams. If an additional couple moment is applied at C, then how will you change the free body diagram of member BC at B? So the idea is, in addition to this 2,000 Newton load, we're going to add a couple moment. And you know when you add a couple moment, what that is? A couple moment is what? What is a couple? Two forces equal and opposite separated by some distance d, right? So I always like, when you see a curly Q on a member, you can always think of that thing as two forces in equal and opposite orientation. So that means you could think of it as something like that. Because otherwise they seem like this mysterious thing, but you can always change them into that, right? And there was one test I found from some, I don't know, it was like Arabia or something, I forget where. And they drew couples like that. They didn't use this curly Q because that is, I think, kind of a little bit weird. They drew it like that to show you that was a couple. It's actually just two forces equal and opposite. So you add one of those at C on that member BC, and what happens to the diagram of member BC at B when you do that? In other words, what happens here? A, B, C, or D? Somebody? B, two forces BX and BY. How many people think B? Okay. Jose, what do you think? You think it's going to add a moment at B? Okay. Matthew, what do you think? D2? 70, what do you think? Come on, you got to decide. B or D? Or one of the others? D? Okay, you're all wrong. Yay. Okay, it's A. Why A? It doesn't have anything to do with it's a couple. What does it have to do with? Why is it A? It changes the force, but the free body diagram doesn't change. Yes, the force would increase at B, But the direction, does the direction of the force change? Because what is member AB? A two-force member. Are you getting tired of me saying that? Well, why don't you remember that? It's a two-force member, so the direction is fixed. It has to be in the same direction. So you can't have a separate two forces, bx and by. By separate two forces, bx and by, that means they're sort of independent, means the direction is not the same. You still just have one force, one unknown, FAB, FB. Thank you very much. Moving on. The figures show a frame. If an additional force is applied at D, how will you change the free body member BC at B? First person to answer is Jose. So now we're adding a additional force at D. So we're adding a force here. How does that affect the joint right there? B, you have a two forces. Yes, because it is no longer a two force member. Yes. These are really great questions, aren't they? Man. You're just going to love taking the final. Okay, so these examples now are on the next sheet, and these are a little more involved because we now have situations where you can have like three things coming together at one point. For instance, the pulley at E kind of has a lot of stuff going on there at E, right? This point here, because you've got member CDE coming in there, you got BE there, and you got this pulley. So there's three things there. Remember when I told you when you have like three things coming together a joint, it's often helpful to do what? Now, draw the diagram of the pin, because the pin is where all those three forces are going to have to balance out. The three different members coming together, those forces are going to be all distributed across that pin, and they're going to add up to 0. So that kind of thing is important. But we're going to solve this thing, this whole thing from scratch. And basically, these are complicated, so we'll take what we can get. The easiest thing to do to start with is let's look at these reactions. What do we got? What kind of support is at A? And what kind of reactions? AY and AX. Could there be like just one? Like could there be a two force? Is there a two force member in here? Where's a two force member? Let's get that up. Get that straight, right? Sorry? BE is a two force member, right? Good. But is member ABD a two force member? No, right? So then we're going to have a separate AX and an AY here. Okay. What kind of a support is here at C? That's a roller. So we're just going to have a CX there, right? CX. The weight is 120 newtons, so you have 120 newton force out there. This is or 100 millimeters or 0.1 meters. Oh, this pen is annoying too, so I can't find the eraser very easily. In order to get this going, we can find these reactions, right? We only have 3 unknown reactions. We can solve those with the equations of equilibrium for the whole body. So the free body diagram for the whole frame is, I've already done it. I've sort of marked up all the forces on the whole frame right here, the AX, the AY, the CX. And you got that 120 Newton force pulling down there, right? So we can solve those and say, okay, the sum of the FYs equals 0. So that's going to equal AY minus 120 newtons. So therefore, AY equals 120 newtons, right? The sum of the moments at A will allow us to find CX, right? So we're going to have CX times the moment arm is what? Yeah, let's put it in meters. CX times 0.4 meters minus the moment from the 120 Newton force is the moment arm is going to be what? Actually, it's wrong. What is it really? You're off by a little bit. It's 0.7. Because that pulley's making it stick out a little further, right? So CX, my answer is wrong. CX is going to be 120 times 0.7 over 0.4, right? Oops, right there. 20 times 0.7 divided by 0.4. It should be 210. And it should be positive. Finally, the sum of the fx's will allow us to find ax. That's going to be cx plus ax. So therefore, ax equals minus 210. So those are the easy ones to find. Now we want to do a little more involved work of breaking apart that frame and solving the internal forces. Actually, all we actually are asked to do is find the forces on member CDE. But in order to get there, I think we're going to have to go and do some of these other ones. So let's start by looking at ABD. So those reactions we just found are applied there. We already found those, so we can just do those. We've got a tension force acting somewhere on there, 100 millimeters up, I guess halfway between there and this pin at B, which is going to have a force on it as well. And since BE is a two-force member, how many unknowns are involved at that point? Just one. We can say that it's in tension. I don't know if it could be tension or compression. And at D, how many unknowns are there? How many reactions are at D? Two, right? Because CDE is a two-force is a multi-force member as well, right? It's not a two-force member, so therefore it's going to have two, a dx and a dy. So how many unknowns do we have at this point? We've already solved for ax and ay. Could we find all of the forces on here? 70? What about CE? What? C. Can you say that again? CD? CD? We don't know about C. When we're looking at member ABD, there is no C there. But I mean, the force is dx and dy, which relates to what's going on that member. It's not a two-force member, though. Is that what you're saying? Why didn't I draw a force here like FCD? Well, because this is one long beam here. It's not a two-force member. If it was a two-force member, I would do that. But you see that there's 3 pins on C, D, and E. So that means it's a multi-force member. If it was just like a separate thing like that, then it becomes a two-force member. And then I would have a FCD there that would be pointing right at it or away, right? That makes sense? So this FCD goes away. My question, though, is can we solve for the forces here? And we have to go kind of fast, so I might not be able to take all your questions. Do you have a quick question, Elariza? Okay. Can we solve for all the forces here? Why not? How many unknowns do we have? We solve for ax and ay. What are the unknowns now left? What's t? How many unknowns do we have then left? 3. Can we solve them? Yes, we could. So we could start here if we wanted to. Just keep that in mind, right, when you're doing these things. Yeah, 3 unknowns, I could do this. Okay. Doing member CDE is this thing here, right? This thing has forces acting at C, which is CX. What about the forces at D? Equal and opposite to the one above it, right? So you're going to have a dx going this way to the left now, and a dy pushing down. And you're going to have an ex and an ey, and given all the complexity that's going on here at E, we're going to want to say that that's a independent ex and ey. Well, with a pulley, no. I mean, if a pulley was just like if there was nothing else there, okay, and you had a tension here, then you would know that direction of that force is at like a 45-degree angle, right? Right? Kind of, because you're going to have a force going that way, a force going that way if you cut those ropes. But because you have this other guy there, that kind of confuses everything. So you have 2 unknowns at E. So we already found CX. How many unknowns are left on member CDE? Can we solve? Got 4 unknowns, can't solve it, right? We know CX, but there's still 4 unknowns. So we can't start at CDE. Let's keep on doing these just for practice, though. We can diagram member BE. It's going to have this force. Well, if FBE is tugging this guy here, ABD to the left, then it must be feeling a tug to the right, or whatever, the opposite sense, right? And this guy should be going in the opposite of that, right? So that's your FBE. And you're going to have the pulley, which is going to have a 120 Newton force here, and the same tension here, which is 120 Newtons because it's frictionless. And the pulley is getting its own force to oppose that, right? Remember, we talked about the pulley, and it is sort of, these are equal forces because of the nature of the pulley, PEX and PEY. I gave it a different designation than EX and EY because there's a lot of, like I said, there's a lot of things going on there at that pulley. Okay, and let's see. So it can be helpful to do, like I said, these are the things where, sometimes it can be helpful to clarify what's going on by actually doing a diagram of the pin. The pin at E is dealing with forces from member BE, from member CDE, and from the pulley. Those 3 things are coming together at that one point. And so it can really help clarify things by drawing out what these things are doing, right? So that pulley is feeling, that pin is feeling a down. So if the pulley is feeling an upward force from the pin, then the pin is feeling a downward force from the pulley, right? So PEY is pushing down, right? Likewise, PEX is pushing to the left. The opposite of what the pulley is feeling, right? You with me so far? And we've got this FBE, which is, on member BE, we're tugging member BE to the right. That means the pulley must be feeling an FBE tugging it to the left, right? We also have on member CDE, we have an EX and an EY, and so the pulley must be feeling the opposite of that, right? If the member CDE is feeling a pull to the right, then the pulley must be feeling a pull to the left. So we also have this kind of, that's supposed to be a straight line. EX going to the left here, and we have an EY pulling it down the pin, right? So it looks something like that. This is like, it may be really kind of a bit much, might seem, but it's actually very systematic. It's following the same principles of equal and opposite, you know, when you move from one body to another, when they're connected, how the forces actually must be aligned, right? And when you see that, it sort of clarifies everything to me, because this is where they all come together. So we're out of time to do the actual equations, but when you look at it as a whole, looking at the big picture, where would we start the analysis? We're trying to find members, the forces on members C, D, E, but there's too many unknowns on members C, D, E here, because we only found CX and we got DX, DY, EX, and EY. We got 4 unknowns, so we can't actually solve for it there. So where would we start the analysis on this problem? Pardon me? A moment around D? E? A moment around D? Around E would have a dy and a dx component. You'd have 2 unknowns still. So the trick is to see that we have to start at member ABD, because that only has 3 unknowns. Once we solve for dx and dy on member ABD, then we can move those dx and dy's to member CDE. Then we only have 2 unknowns, EX and EY, to solve. We can solve those, right? So it's kind of like doing a Sudoku, you know, where you have to fill in the boxes over here, or a crossword puzzle, you know, filling in the boxes over here helps you fill in the boxes over there later. That's the kind of process of doing a frame. It's a really fun kind of process to kind of chip away at the unknowns until you can get to the point that you're trying to find. No, you don't need to find the forces on the pulley, and the forces on the pulley are pretty obvious, right? What's PEX? What's PEY? Yeah. So I'm going to leave this here, and we will pick this up tomorrow. We have one more lecture. So the lecture is kind of, it's probably good to have the time where you can ask these questions and stuff and think these through. But we're going to do this one, and then we're going to do a pliers problem, which is similar. But again, knowing how these things work, really super valuable. You got to have this down when you transfer. You're going to be mechanical engineers. You got to be able to do this.